Hello, my name is Claire Talbert and I am an undergraduate senior studying Geography and Environmental Resources at Southern Illinois University. I have a dual specialization in Sustainability and GIS, and today I'm presenting the preliminary findings of using deep learning models in ArcGIS Pro to extract road culverts from imagery. Using deep learning in ArcGIS Pro to detect culvert locations on high-resolution digital elevation models is tied to the concept of hydrologic connectivity. Hydrologic connectivity is critical to understanding a wide range of environmental management issues such as nutrient transport and aquatic species passage. The spatial characterization of hydrologic connectivity often involves the delineation of hydrologic features using high-resolution digital elevation models. And although there are benefits to using HRDEMs, numerous studies have shown that hydrologic delineation of features like drainage paths and watershed boundaries based on HRDEMs are susceptible to a large amount of artifacts of topographic variations, including flow barriers and depressions. Research has shown that incorporating hydraulic structures can improve the spatial accuracy of the derivatives of HRDEMs. However, manually identifying culvert locations is time and labor intensive. The objective of this research is to develop an approach for automatically identifying culvert locations using computer vision and deep learning, and the model training will be implemented using ArcGIS Pro. So just a little background on deep learning. Deep learning is a subset of machine learning techniques that mimics the behavior of the human brain based on layers of neural networks. One area of artificial intelligence where deep learning has done well is in computer vision, which is the ability for computers to learn from images. It improves the efficiency and the automation of tedious visual tasks, and deep learning in ArcGIS Pro can be used for image classification, object identification, and object classification. So these are some of the tools for deep learning in ArcGIS Pro. Image classification assigns an image or a class to an entire digital image and can be used to categorize features in an image. So in the first two examples, there's a drone image of a crowd and an image of a cat, and those entire images would be categorized as crowd and cat. And this is a little different from object detection, which locates objects within an image, and a bounding box is drawn around the object of interest, and neural networks learn how to locate those objects within an image, and instead of the entire image being classified. Two other tools are semantic segmentation and instance segmentation. In semantic segmentation, each pixel is classified as belonging to a particular class, and this is often used to make land cover maps. Instance segmentation gives a unique label to every instance of a particular object in the image, and it is a more precise version of object detection. A boundary box is drawn around each instance of the object. The study area for this project focused on the Sand Creek watershed in Nebraska, but the later part of the study will use Illinois also as a study area. So this slide shows the general workflow of the deep learning model. DEM data needed to undergo pre-processing in order to conform to the input requirements for the deep learning model. And these requirements are that the input should have a bit depth of 8 bits and have 3 bands. So using the copy roster tool, the bit depth for the DEM samples was converted to an 8-bit signed roster. And in order to make the DEM a 3-band image rather than a single-band image, I used the composite tool to add bands 2 and 4 from corresponding aerial photos. And I used these 2 bands specifically because they were able to best distinguish between vegetation and the drainage structure. Once all of the image samples were processed, I used the Mosaic to New Raster tool to create one raster image with the processed DEM samples. And I then labeled the objects, exported the training data, and then trained and tested the deep learning model. So this is an example of what the image processing for each sample looks like. So the DEM image and then the 2 bands from the aerial images were combined using the composite tool to create one 3-band image sample. And this slide shows what labeling the objects with the label objects for deep learning tool looks like. So culvert locations were labeled using a rectangle boundary box, and that was done for each culvert location. This export training data for deep learning tool converts labeled data into a training data set for the deep learning model. The output is a folder containing image chips that contain the feature of interest, as well as a folder of metadata files, which are both needed to train the deep learning model. So getting into the specific parameters of the object detection model, the sample size was about 100 samples. The model type used was You Only Look Once version 3. This is one of the most popular series of object detection models, and it's a one-pass detection model in which it detects objects in the single pass of an image. And this is a little bit different from other versions of, or other types of object detection models. One is the sliding window, in which the model chooses a region of interest by sliding a window across an image and detecting an object in that region. And a region proposal network, which extracts region proposals and uses convolutional neural network features to classify the proposed regions. It also has a DarkNet 53 backbone model, which is a little bit different from other object detection models that use a ResNet family of backbones. The DarkNet 53 backbone model has 53 convolutional layers and has improved accuracy from previous versions, and it's also said to be more efficient than some ResNet models. So the maximum number of epochs was kept at 20, and an epoch is when the training data are passed through the neural network one time. The batch size, which is the number of images used in every epoch to train the network, was kept at the default of 16, and the validation percent, which is the percentage of training samples that are used to validate the model, was kept at 10%. So like I said earlier, the model was trained with about 100 image samples, and I processed a DEM to use as the test image for the model to identify culvert locations. So I did try this on an unprocessed DEM and an image mosaic of culvert location image samples. However, both of those were unsuccessful, so I had to process this test image in the same way that each image sample was processed. So it had to be an 8-bit signed raster and have 3 bands. So I did the same band combination for this test image. So on this image, I circled a couple of examples of culvert locations that the model, when applied to this image, should be able to identify. So the image to the right shows the ground truth dataset, the label, and the predictions given by the model. So these preliminary results show that the model overestimated culvert locations and mislabeled certain locations. It labeled locations as a culvert where no culvert was present, which indicates that this model did not have a high accuracy in predicting culvert locations. This is the loss curve for training and validation loss. The curve shows that error for both the training dataset and the validation dataset decreased over time. The validation loss began to stabilize somewhat near the end of the graph. However, training loss does not stabilize. This indicates that the model needs to learn more from training data, so it needs to have a larger training dataset. Also, because the validation loss is lower than training loss, this could mean that the training data is more difficult to model than the validation data, or that the validation data is not representative of the entire data set. So the main reason for these results, these preliminary results, are likely because the ground truth data set of only 100 samples is not large enough. So each sample had to be processed individually, and there was a time constraint, so that led to only 100 samples being able to be processed and used for this particular model. And in the next round of testing, I will make this data set larger. So there's no set quantity for the size of the data set to train a deep learning model, and it often depends on that specific data set. However, the general rule of thumb is that the model's accuracy will improve when the data set is trained with a larger amount of data. Since the model has more data to learn from, it can more accurately make predictions about the data. The model's overestimation of culvert locations could also be due to including too large of an area in the labels, so the model could not easily differentiate between the spectral differences of culvert and non-culvert locations. So in the next round of testing, the labels will include less area of, for example, vegetation. It may also be useful to add a class with no culvert location, so the model can differentiate between the presence and absence of culverts, and also changing the hyperparameters like batch size and number of maximum epochs can improve the performance of the deep learning model. In general, studies show that a larger batch size improves a model's accuracy, and it's often a multiple of 32. And choosing a batch size that is too small could introduce a high degree of variance within each batch, as it is unlikely that a small batch would be a good representation of the entire data set. Increasing the number of epochs could also improve the model's accuracy, though this will mostly be determined through trial and error. Deep learning is highly relevant to automating the identification of culvert locations and improving hydrologic connectivity on high-resolution digital elevation models, and this model was able to be trained, although it did overestimate culvert locations. This shows that deep learning can be applied to high-resolution digital elevation models, though processing of the data inputs is necessary before a model can be trained. And this particular model overestimated culvert locations and mislabeled objects on the test image, and this indicates that the hyperparameters need to be changed and the ground truth dataset needs to be increased. I do have some research updates from when I presented at the Illinois GIS Association conference in October. So the ground truth dataset now contains 223 image samples, and image samples with no culvert present were added to the dataset so that a no culvert class can be incorporated into the new deep learning model. And this can be helpful so that the model is better able to distinguish between where a culvert is and is not present, and this could decrease the number of misclassifications. For now, the maximum number of epochs will be kept at the default of 20, since this is a small, this model has a small dataset. The maximum number of epochs should be kept at a low number. However, the batch size will be increased, as I said previously. This can help improve the accuracy of the model. Although both of these, the maximum number of epochs and the batch size, will need to be tested on a trial and error basis and can be changed based on the results of the next round of testing. And for the next model, the validation percent will be increased to 30%. So 30% of the samples will be used as validation data. And this is pretty standard for a small data set. So very soon, a new deep learning model will be trained with the improvements that I mentioned earlier to the hyperparameters and with the increased data set. Based on those results, if the data set still needs to be increased, image samples can be shifted or rotated and trained as new samples, which increases the data set and hopefully will make the model more accurate. And then beyond that, further processing would include extending drainage crossing using a least cost carving approach when culvert locations are identified, and developing hydrologic features using processes like sink filling, deriving flow direction, determining flow accumulation, and deriving an ordered stream network. These are my references, and a special thanks to the National Science Foundation and Southern Illinois University, as well as Dr. Lee and Dee Wu, who advised me during this project. So please let me know if you have any questions, and feel free to contact me at this email.
I don't know how they can hear me, but okay. Oh, cool. So
Rita Castro has a question. What size were the culverts that were part of the study? Claire, if you could unmute yourself and answer that, that would be fantastic. You're still with us?
Yes. Can you hear me?
Yes.
So I got this data set from like my professor and another project that was going on. So I'm not sure what size culverts were used, but if you email me or if you give me your email, then I can find that out.
Okay.
And I would be happy to figure that out and email you with that information. I could put my email in the chat again if that would be helpful.